All right, so last time we left off on physical properties. Okay, so these are going to be characteristics that are going to be observed or measured without changing the identity of a substance. Oops, that is not on. Thank you. Did I get it this time? Yes, I did. Okay. Okay. All right. So, some of the physical properties are going to include things like shape, physical state, boiling, freezing points, density, color of a substance. Can anybody list a physical property of something around you?
Texture.
You got it. Texture is a physical property. Exactly.
Boiling or freezing points.
Boiling and freezing points. Exactly. So smell, the ability to smell it is a physical property. The actual smell itself would be a chemical property.
Because you have to physically be able to touch it or see it.
Yeah, so when you smell something, it's because it's semi-volatile, and it means that some of the molecules made its way up into your nose, right? And then you actually have chemical sensors in your nose that are going to trigger when they detect different functional groups on it. Yeah, and so that one is actually a chemical reaction that happens in your nose. So, yeah, I guess that one's somewhat of a complicated one, right? So copper here, these have these physical properties. We have the reddish-orange color of this metal right here, which shiny. It's an excellent conductor of heat and electricity. It's solid at 25 degrees Celsius. We have a melting point that's 1,083 degrees Celsius and a boiling point that's 2,567 degrees Celsius. And so that's why, for example, if you ever look at something where you're trying to rapidly cool it, it's usually made out of copper when it touches it, right? Or you might have copper as like wiring, right? Because it's a good conductor, exactly. Yes, it's one of the more expensive wirings, though. Did you know that the better wiring is actually gold?
Yeah, but you can't.
Oh no, they do.
Well, that's why like a lot of your appliances, like the ovens and stuff, they have copper wire.
They do, exactly, because they have high amperage, and so it doesn't heat up as much when it's conducting the electricity. And then things that, it doesn't matter for, or it's low amperage, they'll start using things like aluminum wiring, or they'll use iron or steel wiring. Yeah. Interesting side note, if you actually were to open up computers, high-grade computers, has anybody ever seen a CPU? The bottom of a CPU? If you look at the bottom of a CPU, it actually has hundreds of little gold wires sticking out. And they use gold because they need it to be that efficient. Okay? All right, so physical changes, these occur when matter undergoes a physical change of state, but its composition remains constant. So, for example, we've seen all three examples of water in pretty much our daily lives, right? So we've seen ice, which is the solid form of water, right? We've seen water or liquid water, right? And we've seen steam or vapor. And everybody can see those different examples on most days. Specifically if you look up into the sky. Okay? The really bright or dark clouds, those are actually solid particles. Okay? The lighter misty looking stuff that just sort of shades or shimmers, that's the vapor in a fairly concentrated form. I'm sorry, not the vapor, excuse me. That is the suspended liquid particles. Okay? And then, of course, everything around it right now. We're in Tennessee, so there's a fair amount of humidity right now, right? So all around us right now is water in the vapor form. We can't really see it very well. By the way, when you look at the exhaust of a power plant and you see those white plumes coming out of it, or the exhaust out of your car and you see white plumes coming out of it, or shimmer, what is that?
That's carbon monoxide, right?
Nope, it isn't. No, that's what they always use. So you're thinking of the articles that you always see, and that's always what they say it is, right?
It's a vapor.
It's not a vapor, actually,
Okay.
which is funny.
Gas. I
It's not a gas either.
No, it's the liquid particles.
It is. It's the liquid or solid particles of water. So those are literally plumes of water.
Yeah, it's not actually.
Yeah, it's the black stuff coming out that would be like carbon bodies that be on burn fuel, and that means something bad's happening to the plant because they do not want to do that. It's a real waste. But yeah, the newspaper articles always use those pictures because they look very striking, right? And then they say like carbon monoxide or pollutants or it's always wrong. They're just using a sensationalist picture. Has anybody seen a picture of the Great Garbage Patch? No? It's the patch of plastic in the ocean. It's the size of Texas.
What's it called?
The Great Garbage Patch. Okay, those are not pictures of the Great Garbage Patch. The Great Garbage Patch is not actually visible. The plastic floats slightly below the water, and it's a very thin layer actually, and so you can't actually see it in any way that actually is useful.
How do we know where it is?
We can detect it, of course, because it's below the water, and so like we can go around it and go, yep, plastic, yep, plastic. But you would have to do that or actually use special instruments like Raman spectroscopy works. We have Raman spectrometers that float around the Earth, and we can ping.
So we can still figure out where it is fairly easily.
We can. It's just not visually striking at all.
So we can still find it, which means we could still technically clean it.
Oh yeah. We definitely could. Though the amount of resources that you'd have to pour into that would actually have more adverse outcomes than the Great Garbage Patch itself.
What do you mean? Can you just like send a bunch? Can you just send like a whole bunch of cargo ships with giant nets and keep going at it? It doesn't have.
The nets break, and the majority of the Great Garbage Patch is plastic nets. So it's like that's actually 50% of the plastic in the ocean.
The plastic nets would still get caught up in the nets that get.
Yeah, and then they break them because their weight's greater than the net itself.
Okay, well don't use plastic nets.
Yeah.
Like, use metal leaf nets.
Yeah, we should talk about it sometime. It's kind of an interesting conundrum, and there are projects trying to do it. None of them have actually shown any proof of concept that they could succeed, despite they've put in a few billion now in this. Yeah, it's a messed up situation.
Isn't there substances that can dissolve plastics and stuff? Can
Nope.
you just dump a whole bunch of them in the water?
Oh, yes, but you'd kill all the life in that entire area of the ocean.
Is that more or less life than would be killed if we just left
Oh,
the
no.
patch alone?
Nope, the garbage patch is not actually particularly harmful or lethal. Yeah. So it's actually, it's like CO2. Like most of the stuff you can do to clean up CO2 in the atmosphere is actually far worse than the CO2 in the atmosphere. And so, yeah. Kind of like anybody heard about the battery mines for the electric vehicles? The lithium and the rare earth metal mines? Yeah, they have a huge slave problem. They kill all life in the area. If you start looking at the actual global impact of the electric vehicles, right now it's probably actually worse to be driving an electric vehicle. You're actually probably harming the environment overall. But to be fair to them, in 10 years, that's probably going to be completely reversed. Yeah, because the electric vehicles are getting so much better every year. So, and it needs development and needs money. So you can look at it in the future weight. Yeah. Anyways, it's a things are more complicated when you get into environmental science than just clear good and bads. So the chemical properties, these describe the ability of a substance to interact with other substances to change into new substances. When chemical change takes place, the original substance is turned into one or more new substances with new physical and chemical properties. Think of it like this. Before physical changes, I was just changing water from one thing to another, right? Breaking it up, making it steam, can come back into liquid water, right? And chemical changes, they're not going to be easily reversible. It's going to be very difficult to do that. So they're going to be taking water, and all of a sudden I have I might have hydrogen peroxide, or I might have hydrogen gas and oxygen gas, right? It's a completely different compound, a completely different substance, right?
So like salt.
Yeah, like salt versus the chlorine and sodium, right? Exactly. So during a chemical change, a new substance forms. This has a new composition, new physical properties, new chemical properties. One of the examples of this would be iron nails when they're corroding in the presence of water. They actually form a new substance, and you can pretty easily tell this is a new substance, right? There's almost no property that's the same. There really isn't basically no property that's the same at all, right? And that's rust. And that's actually iron oxide. We can see that right there. Okay? Now, does anybody know, does the rust actually form in the water?
It's on the nail.
Yeah, it's actually on the surface level, isn't it? Yeah. And that's actually because you need exposure to oxygen to form the rust. That's one of the reasons why, like, we can find iron things that were thrown into the ocean 1,000 years ago. It's because they need surfaces where the water is actually excluded to gather the oxygen and rust. And so it actually can get preserved pretty decently. They do rust eventually, but a lot slower than if you expose part of it to oxygen, to the air.
So what if it's deeper than surface rust?
What do you mean?
So you said that it's just on the surface with the rust.
Mm-hmm.
I assume it's still a chemical change even if it becomes deeper rust, like when you see the bottom of a car and it's been rusted out and
Mhm.
now it's affecting it physically though.
Yes. So eventually what does happen, remember that car and items we're actually using can sometimes be a bit of a questionable comparison because they've been engineered with intolerances, right?
Yeah,
Like-
nail obviously is different than the underside of a car.
You ever heard of like the saying that it takes an engineer to make a bridge that just barely stands?
Yes.
A normal person just makes a bridge that'll take like 10 times the load. And it has, 100 times the cost, right? Yeah. So, but yeah, what will happen is that the rust will actually cover it up, but the rust isn't going to cover it up perfectly. In fact, that's actually how aluminum works. If anybody has an aluminum can and they look at it, take that aluminum can, it's kind of a dull color, right? And then you scratch it, and you see a really shiny surface under. And that's because aluminum actually rusts super fast. Okay? You'll actually see it go dull over the course of several minutes. And what you're actually seeing is the aluminum oxide's very, very hard and very chemically inert. And it forms so perfectly that basically encases the aluminum and it can't rust very well. Okay? It will slowly rust though, because oxygen can penetrate. Remember, molecules and atoms are not full, right? They're 99% empty. And so the oxygen can penetrate slowly, and you will get rusting in and in and in. And that's what happens to a car when it rusts out. The rust hasn't perfectly covered it, and so you get oxygen diffusing in and rusting below. Now, the rust does actually slow that down. And so, for example, we find these rusty swords and stuff buried in fields, and the rust rusted perfectly enough around them that they preserved the sword under. They actually recently just found one that was like 800 years old in a field, just sitting there. And it was actually, once they cleaned the rust out, almost perfectly preserved. Yeah. So, this is actually sugar caramelization, and that's flan. Anybody like flan?
Oh, I love it.
And
Yeah, flan. It's European, Spanish does it quite a bit. Anyways, anybody that raised their hand probably has been to somewhere where like it's actually made really well.
Italy.
Yeah. Yeah, Italy makes great flan. Mexico makes great flan. If you don't like flan, it's probably because you didn't have a good one made.
Any plant I love.
Yeah, bad flan is awful. It's all tacky and gross. So, classify each of the following properties as physical or chemical. Ice melts in the sun. Physical. You got it. You got still water, isn't it? Copper is a shiny metal.
Physical.
Physical. Yeah, it's shiny.
Oh, physical.
Yeah. And you could make it less shiny, couldn't you? Just by like roughing the surface. Paper can burn. That's a chemical one. You got it. A silver knife can tarnish. Chemical again. You got tarnish would be a chemical. It's the rusting, quote unquote, that silver does, right? Yeah. It's not actually oxygen doing that, by the way. Yeah. So a magnet removes iron particles from a mixture. Physical. You got it, because you could always mix them back up, couldn't you?
Okay, yeah.
Yeah. And it's not like the iron changed. It was iron. Now it's still iron. Okay. So here's temperature. I'm going to tell you the book's definition of things, and then if it's problematic, I will tell you a better definition, okay? Temperature is one that is a bit, it's okay-ish. So this definition is a measure of how hot or cold an object is compared to another object. It's measured using a thermometer. Of course, you can measure temperature in other ways. Actually, thermometers are not widely used anymore. What is actually used now is conductance. Yeah. And that's the thermometer, quote unquote, that you've been using, almost certainly. Yeah. We'll use actual thermometers sometimes in lab. And actually, the mercury ones are amazingly good, but we never give them to you guys anymore. Because mercury is so hard to get rid of, and like mercury spill happens, and all of a sudden the university's spending $200 to $1,000. Yeah. So it's measured and reported typically in degrees Celsius if we're talking about metric or science. Kelvin is used fairly widely. Funny, interesting little fact, back in the day, early works used to be done in degrees Fahrenheit because they were French, and the French used to use degrees Fahrenheit. So all the old data is all in degrees Fahrenheit. So I will give you a bit better of a definition for temperature that will actually make temperature make more sense. So what temperature actually is, it's a measurement of randomized kinetic energy. So kinetic energy moving in all the different directions. So you can't just calculate, oh, they're all moving in the same direction this way. Okay? And so when you start looking at temperature, if you have a higher temperature, you have a higher average kinetic energy in that area, right? If you have a lower temperature, you have a lower average kinetic energy. Things are not moving as fast. Okay? Is that making sense? Yeah? Okay. Okay. It actually makes everything about temperature make far, far more sense, right? Once you start thinking into it. Yeah. Temperature scales. We have, of course, the Fahrenheit, which is what us dang USA people use, and funny enough, people that tend to typically trade with us a lot and do stuff with us a lot sometimes get their temperature scales and stuff hijacked by us and end up using the same thing. I always think the Canadians are funny because most of their people live on the border, right? And so a lot of their news stations are American, or funny enough, Canadians usually say American too, so I guess whatever. But are USA stations, and so like they use dual units for everything because they just have to do the US stuff and the Canadian stuff at the same time all the time. So poor Canadians. I guess we're pretty annoying in that sense, huh?
I have a question. Is Fahrenheit, did that come from like Germany? Oh, it just sounds like German.
I actually don't remember where Fahrenheit came from.
Originated in Germany?
I think it came from actually French.
Okay.
Most of the units from this time period came from France.
Okay.
Germany doesn't really start coming into chemistry much until about the like late-ish 1800s.
Okay.
Yeah, and then up to about into World War II. Yeah.
Okay.
Do you guys know? Did I talk about Blitzkrieg at all?
No.
No. So, you know, Blitzkrieg, German army. That's a very famous thing, right? That was their innovation in World War II. So the reason that Blitzkrieg could even happen was because they used to take essentially what would be like a derivative of speed or meth. And so the soldiers would actually have little pill containers that would have what is essentially meth. And they're popping that, and that's how they can go 3 days running behind a tank.
They did meth?
Basically, yeah. Yeah. It wasn't actually meth. It was a bit more of an advanced drug with a bigger, better effects with slightly less worse side effects. But yeah.
That actually does make sense because the only thing about meth that doesn't make it perfect for a military situation is the fact that people tend to go out of control when they're on it. Everything else about it would be perfect in that sort of situation.
Of course, the German soldiers after that first stage of the war started getting addicted, and yeah, that's part of why they went so crazy and so out of control. But
Kelvin comes from Great Britain.
Yep. Kelvin comes from Great Britain. That's exactly right.
That would be a cool ass name.
That's
It
what
is. It literally is. So I was going to talk about that. Mm-hmm.
And the only reason the
Oh
Blitzkrieg
my God,
didn't work
that's cool.
was because they tried to do it to Russia during the winter and got stopped by General Winter. If they hadn't turned on Russia, they may have actually won.
Yeah, maybe. Okay. Good thing they didn't, though, overall.
Yeah.
Yeah. Anyways, so Fahrenheit goes 32 degrees is the freezing point of water, and 212 degrees is the boiling point of water. If we look at Celsius, Celsius has 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. Now keep in mind when we look at Celsius, that degree symbol means that 0 is an arbitrary number. Okay? It's arbitrary in the sense that your exact freezing point of water actually changes depending on the pressure. And so we basically went under these conditions, water freezes at this temperature, that's the 0. Okay? Yes, that temperature is actually slightly off. Because when they set the number, it was not actually, they couldn't measure that precisely, right? So, Kelvin, on the other hand, had to be born. So, Kelvin, that's a person, discovered that there is a 0 to temperature. If particles weren't moving around, they were frozen in place, what would that be?
0.
A 0, yeah. 0 Kelvin. There's no randomized kinetic energy if everything's frozen in place, right? Or another way of saying that is if everything's moving the exact same speed and direction, that's also 0. Because they're no longer random, right? They're all coherent. They're moving in the same direction. That's actually how they get most of those measurements, by the way. That you see like 0.0000 something kelvins. That's how. They just shoot everything in the same direction. Freezing things is actually very difficult to do. So that is 0 Kelvin, and if we go up to 0 degrees Celsius, that is 273 Kelvin, i.e. the freezing point of water, 273.15 Kelvin. Notice the lack of a degree symbol for Kelvin. Why would that be? Yeah, it's not an off of an arbitrary point, is it? It has an actual 0. And that's a universal constant. Okay, so this is the normal body temperature, by the way. You all may recognize this one, 98.6 degrees Fahrenheit. That's 37 degrees Celsius. That would be your normal body temperature. Okay? Okay, does anybody have any questions about these? All right, I will give you a bit of a formula to convert between the two. Personally, I kind of just remember them based off of this and work my way back in the formula. And so 100 degrees Celsius covers 180 degrees Fahrenheit. And then you have to add 32 to it. Because the freezing point of water is 32. I find that easier to remember personally. But I'll give you an actual formula. So on the Celsius scale, you have, of course, 100 degrees Celsius. That's the freezing, the distance between the freezing and boiling points of water. The 180 degrees Fahrenheit would be that same distance. 180 degrees has to equal 100 degrees Celsius. And so that works out to 1.8 times 1.8 degrees Fahrenheit divided by 1 degree Celsius. Now note, the freezing point of water is what on Fahrenheit? 32. So if you want to convert these, if you want to go into degrees Fahrenheit, you're going to equal 1.8. And then this is going to be multiplied by your temperature in Celsius, right? And then this is going to be plus 32.
Why is it 1.8?
So that's the
It's 180 divided by 100. And so you can put that in the calculator or simplify that. That's 1.8 then over 1.
And then you do that.
Yeah.
So that's the formula you're telling us you're going to give us, right?
Yeah, that's the formula right there. It's also in your book. It's also later in my slides. I'm just going to go ahead and put it here because it's easier. People don't get quite so confused. All right. Yeah, and you can use that formula, of course. Then you have to have a formula written down in your notes, or you have to memorize it. Okay? Okay, so what temperature is the temperature at which water freezes? Yep, it's 0 degrees Celsius, right? Okay. So what is the temperature at which water boils? Okay, so what temperature would water boil? We have 100 degrees Fahrenheit. We have 32 degrees Fahrenheit. 32 degrees Fahrenheit is freezing. That's the freezing point of water. This one right here can't be the boiling point of water because 100 degrees Celsius is the boiling point of water, right?
Okay, 373.
Yep, that's 373 Kelvin.
So you told us that Kelvin, 373 is 100 degrees Celsius or 200 degrees Fahrenheit. 212 is the boiling.
That was right there, right? Okay. So another way of thinking about this is 100 degrees Celsius, boiling point of water. We could add 273 to that. That would also get us there, right? Okay, so how many Celsius units are between the boiling and freezing points of water? It's 100. You got it. How many kelvins are between those 2 points?
You said between the freezing and boiling is 100.
Boiling and freezing point? Yep, it's 100. So kelvins and degrees Celsius, those actually have the same changes, don't they? Yeah. Basically, kelvins was in place, or Celsius was in place. Kelvin was born when that zero is arbitrary. I figured out this has an absolute zero and shifted the whole scale down.
So you can never go past 0 Kelvin, correct?
Nope. You can't have anything lower than 0 Kelvin. Yeah.
So if you found something colder, then you would have to go on what, Fahrenheit or Celsius? Or is
If something colder existed, we would reset the 0 Kelvin.
okay, because I know it's like negative 470 degrees Fahrenheit.
Yeah. That's actually the lower bounds. Nothing can be colder than that because there is no backwards
Okay.
to not moving in place, right? Yeah.
So Kelvin can't be negative either.
Like you can't be more still than already still. Yeah. And so, yeah, no negative Kelvin. If there ever was a negative Kelvin found, we'd have to lower that temperature. It's kind of like the speed of light things. If the speed of light was ever found to be faster than the speed of light, then the speed of light would just change that number, right? Yeah.
Body temperature, freezing point.
So what is the...
Wait.
You okay?
Oh, no.
Okay. Okay. This is the formula I just had given you before. That's the temperature in Fahrenheit equals 1.8 times the temperature in Celsius plus 32. Note that if you solve the formula to the reverse, that is that right there. So, for example, if you wanted to find temperature in Celsius, you could go backwards in that formula like so. All that is just doing the math, right? That's algebra. Okay. Okay, please let me know. Actually, try these things out. I would recommend having this somewhere in your head. Did you know by treaty, the United States is required to have its middle school students know these conversions?
Wow, big tree.
Yes, by treaty. We made a treaty with all the other countries in the planet. Well, all the ones at the time that it's like 100 countries. So most of the countries in the planet. That we would convert to the metric system in the 1980s.
We didn't keep that.
And in that treaty, which is still in effect, we were required to teach conversions between imperial and metric in middle school. It's also is on the middle school testing that you're supposed to be done, and that is actually something that's supposed to be taught at schools. So that's actually kind of a funny thing that don't feel bad if you don't know them, because like most of the U.S.
Obviously didn't have it.
No, we are totally in violation of treaty. Did you know that Russia is actually by treaty required to come to the defense of Ukraine
What?
if it's invaded?
Yeah.
Does that
From
mean
an
they have to
outside-
fight themselves right now?
They do. By treaty, they're supposed to be fighting themselves.
Oh my god, no, I
Yeah.
want to see a
It was the
revolution
when we
based on that.
disarmed Ukraine's nuclear arsenal, both countries wanted it not there anymore. And so we both did a self-defense treaty with Ukraine to do it. So we're also supposed to come in full warfare and go after anybody that goes after Ukraine.
Now I want to see some Russian general decide that he can do better than Putin and base his revolution against him off that treaty.
Kind of already happened, but anyways. So the typical temperature in a room is 21 degrees Celsius. What is the temperature in degrees Fahrenheit? Okay, let me point out a lot of the questions are multiple choice. I'm going to basically give you tests that are multiple choice because that's the only way I can do 44-ish students. So, if I have a multiple choice question like this, is there an easy way to do this question? What's room temperature?
21
What would-
degrees Celsius?
No. If I'm doing room temperature in Fahrenheit, what would room temperature in Fahrenheit be, considering I'm an American and I've been using Fahrenheit my entire life and setting thermostats?
So let's say 70, 60.
Yeah, let's say 70 degrees-ish, right? And so what do you think the answer is?
I mean,
68.
it's set.
Something close to 70 degrees Celsius, or Fahrenheit, right? So the answer is something around 70 degrees Fahrenheit. If I'm given multiple choice questions, yeah, it's almost exactly that, right? Yeah.
So you round it
So
up.
if I'm giving, no, what I'm saying is that you don't actually even have to do the math if you're given a multiple choice question. You literally know what a room temperature should be, right?
Between 68 and 70 is what it's
My mom keeps it at
Yeah.
78,
Most people would keep it somewhere within a few degrees of 70, right? Multiple choice questions have to have some sort of coverage, right? They can't just all be the same number within 0.1, typically.
I think mine's at 72.
So, yeah, anyways. Like, you all proved my point, but you're nitpicking things and... Anyways. So, that's temperature Fahrenheit equals 1.8 times the temperature in Celsius plus 32 to do the conversion, right? And so we plug our number in right here, the 21 times 1.8, right? We're then going to add 32 to that. And so that is 1.8 times 21 equals 38, right? We add 32 to that. We end up in a number that is just a little bit under 70, don't we? Yeah, 69.8, I believe.
And there's 2 sig figs, so you round it to 2.
Yep, you round up to 2 sig figs, and so it ends up being 70. Correctly stated, it is 70 period, right? Degrees Fahrenheit. So scientists have learned that the coldest temperature possible is 273.15 so far degrees Celsius. Actually, there is a more accurate measurement, but I don't think you need that many decimal places. we do experiments where we basically use different methods to make everything coherent, or we use different methods to freeze everything in place.
Does it mean it's theoretical?
No, it's experimental. Like we've made an experiment where we held everything in place and then we measure that temperature.
Okay, so what's the coldest natural temperature they've ever found?
Pretty close, actually. You can use helium, actually, to get that number that's 273.15. That's actually liquid helium. Yeah. So you can actually get, naturally, if you go into space, pretty close to that. You have to have gases escaping the entire time to get down there. But, yes, you can get pretty close. Kind of like a compressed can, right? Yeah. So, on the Kelvin scale, and on Earth, by the way, you can't get anywhere near close to that naturally without doing something really crazy. Okay. On the Kelvin scale, this is called absolute zero, of course. It's zero represented by 0K. Again, it has the units of Kelvin. A unit of Kelvin is actually equivalent to a degree Celsius. We've just shifted the zero, right? Yeah. And so there are no negative temperatures, of course, as was pointed out. There's no degree symbol. This is actually how you calculate that. You just take your temperature in degrees Celsius, add 273.15 to it. Most of the time, you all will just use 273 because we won't have more than 2 or 3 sig figs. And that's close enough. But 273.15 if you want the extra sig figs. This right here is some different temperatures and a comparison of them. This is liquid nitrogen, by the way, that you've actually seen quite a bit. Notice that the coldest of temperatures that you'd hit on the planet is not anywhere near absolute zero, is it? Yeah. And so you're looking at like a 200-ish Kelvin usually. And that would be a very, very cold winter day. Okay, and so the chemistry linked to your body, we have, of course, body temperatures, and they can vary. This is called hyperthermia if we are above the normal body temperature. This can lead to convulsions and may cause permanent brain damage. Heat stroke actually occurs at 41.1 degrees Celsius. One of the treatments for that is to immerse somebody in a water bath to immediately cool off their temperature. Pretty easy to get that around here because of the high humidity. Your body has a hard time cooling itself when it can't sweat and evaporate.
I'm not sure if this is right, but I read somewhere that's actually better to do that in like room temperature water than it is super cold water, because super cold water might.
It depends on the emergency. So if you are to this point where you're having convulsions, you throw them in an ice bath. And then you can carefully modulate. If you're doing it to yourself on a hot day, just room temperature water body would be fine. So again, it does depend on the severity, how fast you need to do it. Okay. By the way, anybody ever seen the Pirates of the Caribbean?
Yes.
Okay. What's the captain in that movie?
Captain Jack Sparrow.
Captain Jack Sparrow. And what's he like?
Whimsical.
Shaky. He has kind of a weird perspective. He
surprisingly moral.
yeah, surprisingly moral actually. Yeah, for a pirate.
He's hungover.
He's not hungover actually. He has heat stroke that has caused permanent damage.
Oh.
He was trapped on an island for 3 days with booze only, no water.
Hungover would
That
be
is
why he
true.
ever stopped drinking to begin with.
Well, he comes off a boat that wouldn't be able to hold anything, and was already mostly sunk. So, and he's taken over boats, and they wouldn't have liquor on like military vessels. So there's long periods in that movie where he would not have been able to have a drink. And yeah, he for sure had brain damage from that event. Like, you couldn't go 3 days without water on a hot desert island without going through heat stroke and brain damage. And that actually, all the things that he does with the shaking like this and his not being able to complete thoughts and then skittering on to other thoughts, that's very consistent with heat stroke brain damage. So, I know, right? He seems like a Mad Hatter's the same thing. That guy also has nerve damage. Okay. No, that's actually what the character was written for. To exhibit nerve damage. Yeah. From a pollutant, mercury. Yeah, I know, right? So, hypothermia. This can happen at temperatures as low as 28.5 degrees Celsius. So the treatment typically is going to involve providing the oxygen and increasing the blood volume. Typically you do this with glucose and saline fluids. One of the ways you want to do that is you want to inject warm fluids. Because we are directly injecting the warm fluids, they very much do need to be very close to your body temperature. Okay? Because you won't be able to modulate this and we won't be able to remove it fast enough if we were to shoot this up to 40 degrees. Okay? You'd have a lot of troubles. Like 41 degrees, if we injected that into you, you'd be not happy. Yeah. And it's mostly the IV portion of this. It's just not as easy to claw back, right? If we dunk somebody in cold water, it's easy to claw back, right? A person with hypothermia has a body temperature. Hypo means lower, right? Hyper meaning greater. Okay. Has a body temperature of 34.8 degrees Celsius. What is the temperature in degrees Fahrenheit? My only temperature meter was in degrees Celsius, but I'm an American. Oh my goodness. Y'all look at me like this couldn't happen, but it does happen all the time. Like a hospital once almost shut down for 3 days because they got a shipment that only said CC on it and didn't say milliliter. And none of the nurses knew that CC was milliliter.
Why didn't they look up a conversion? What year was this?
This was actually like, I think it was about 7 or 8 years ago.
We had the internet then.
Yeah, we did. But there's large parts of the hospital that don't. Large parts of hospitals don't have the internet because of the shielding and their MRIs. Yeah.
I thought it only applied to the room the MRIs actually happened in.
It's very difficult to get a decent connection in a hospital. Yeah. So anyways, let's write a equation, of course. We're going to take that wonderful degrees Celsius number, 34.8 degrees Celsius. We're going to plug it in and multiply it by 1.8. And so 34.8 divided by times 1.8, equals 62.6. We add 32 to that, and we get 64.64. Thank you. And we round that to 64.6, right?
Because
So the temperature is 94.6.
Yep.
That's pretty average.
It is. It's a little lower, though. And so this person, normally you exist in a pretty tight range of temperatures. Like, you start going down, you're going to be shaking like a leaf, right?
Oh, yeah.
Yeah. And the reason for this is there's actually a pretty tight range that we actually function decently. Once we get even a little bit beyond that range, like a degree or two, you start having a lot of problems. Yeah. Now, cold temperatures are... okay, so most temperature deaths on the planet for humans happen with cold temperatures. Anybody know the ratio?
4 to 1.
Yeah, it's about 4 to 1, 1 in 5 cases. So heat deaths are actually very, very rare. Cold deaths are far, far more likely to happen. Way, 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 way more common. Yeah. And now cold deaths are kind of interesting because they actually take longer to run it out. So you can cool somebody quite a bit and bring them back very carefully. So if it's controlled. Uncontrolled, it can be a different issue. Energy. Energy is defined as the ability to do work and can be classified as either kinetic or potential energy. Anybody tell me kinetic energy? You all shook your head at me. What was that?
Energy and motion.
That's kinetic energy, right?
Like if you hit someone with something, as the thing flies through the air,
It is, and them actually getting hit, and then their flesh changing. That's also kinetic energy.
And rearing back to swing it, that's the potential energy.
The rearing back to swing it is actually kinetic energy,
Okay,
but
tension
that
of your muscles,
tension
that's
of your
the-
muscles, exactly. That's the potential. You got it. And the chemical energy in your muscles, that's also potential. Okay. Anybody give me potential energy?
A rock sitting on a hill.
Rock sitting on a hill, classic example. Or the battery in your phone, right? Also potential energy. Or the sugars, the fats, all that in your body, potential energy. So again, kinetic energy, energy of motion. Potential energy, it's going to be determined by the position of an object or its chemical composition. These are two of the most common ways that you'll determine it. That's a good enough definition for our purposes. We don't really have to go further than that. So, water in a reservoir behind a dam has potential energy. Water released over the dam that has kinetic energy. Very good. Identify the energy in each example as potential or kinetic. Yeah? Oh, stretching? Okay. Sorry for calling you out on stretching. Rollerblading. Kinetic. Very good. Rollerblader on a hill. Potential. Rollerblader when they lose control and fall down the hill. Kinetic. All right. Peanut butter and jelly sandwich. Potential. Eating it is chewing it. Kinetic energy. You got it. Mowing the lawn. Kinetic. Very good. Gasoline in the gas tank. Potential. Very good. And you're going to use that to drive, right? Which is your kinetic energy. Fantastic. So heat. Heat is a form of energy. The units of energy is joules. Okay? So when we start looking at that, remember that. So heat, that's going to be the energy that's associated with the motion of particles. It's going to be the energy that's associated with temperature. Okay? So you can think of it as the randomized kinetic energy. That's your heat. That movement of that is your heat. The faster the particles move, the greater the heat or thermal energy of a substance. Your SI units for heat and energy in general, and work as well, which is a type of energy, is joules, which is capital J. And of course, kilo means 1,000, right? So 1 kilojoule equals 1,000 joules, right? Yeah. Now, I know your book does this all the time. It's actually easier just to remember prefixes to modify units, right? Rather than trying to memorize kilojoules to joules, kilometers to meters as separate things, which would make this far, far more information. So these are some different energies that you might see. So for example, energy used during sleep for 1 hour, that's 10 to the 4th joules. Notice joules is not a huge amount of energy, is it? No, it's actually a pretty tiny amount. The energy of the radiated by the sun in 1 second is 10 to the 26th joules, which is a pretty good amount of energy. Okay. All right. So the unit calorie, this is going to be defined by the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. And so that is a calorie. Now note that the calorie actually is what the joule is defined against. Okay? And so the joule, for example, is 4.184 joules. That is a calorie. That is an example of an exact number, actually. Okay? I know. It's a weird exact number, but it is an exact number. Okay? Remember I was like, exact numbers can have decimal places. There are a few examples. Right here. That's that.
And we never round it off. Always.
Nope. Yep, that's an exact number.
Do you have to memorize that?
I would put it in your notes, personally. Yeah. I do tend to give these things, except where I'm asking you definitional questions. And so that is the risk. you would run. Okay. And so those are the conversion factors, by the way. If I have a capital C calorie on a food packet, by the way, what is that? So on the food packets, there's a unit called calories, but it has a capital C instead of a lowercase c. Okay? That is a kilocalorie. Because people would go, oh my God, what am I eating? If they saw 400,000 calories. Which is like your average soda, right? You imagine looking on the back of your drink, 400,000. Holy. All right, so let's talk about energy and nutrition. One of the major things that you need to intake whenever you're eating is, of course, energy. Being a United States citizen, we take way too much of this in if we're not really careful, right? Super difficult not to. So carbohydrates, these are going to be your primary source of energy in your body. When carbohydrates reserves are exhausted, you're going to start moving on to fats. And then after fats are starting to get difficult to do, you'll start moving on to proteins. Okay? And you will actually start digesting your own muscle mass if it gets bad enough. Right? Or you'll just use up excess proteins if you have them. Okay? Now, fats is actually what you carry around with you, right? It's the jiggly stuff. Okay. You actually do have a store of carbohydrates you carry around with you called glycogen. It's like the starch of plants. It's just more condensed. Anybody know where that's usually stored?
In your,
Yeah, anybody seen a beer belly?
yes.
That's a glycogen store. Okay? And that's why it's different consistency. It's like hard, right? Yeah. It's not flabby and soft. Like my flabby and soft. All right. Now, so that's actually string together carbohydrates you're storing. Now, you do store a little bit of those around your muscles themselves. Okay? It just doesn't build up as fast as like your liver area does. And that's why beer bellies are so bad for you, because they can clog up your liver area pretty bad. But anyways, so here's a food label. Remember that the calorie on the food label, capital C, is a kilocalorie, meaning it's 1,000 normal calories. Okay? Now, if we note this, what do we see about these calories? Yeah, it's 130 calories. If we did real calories, that would be 130,000. And yes, these servings per container are entirely arbitrary. There is no guidelines on what you actually have to do. That's why you get things like one Oreo or half a candy bar as being a serving. Like, who the hell is going to open the package of a candy bar, eat a half of it, and figure out how to store it? Really? That's a thing? Or sometimes they're not even a half of it. It's like a fifth of a candy bar that has no way to store it. Or a soda can, right? It's not even the whole soda can is the serving. You're going to restore it in the soda can? Who the heck's doing this stuff? Anyways, this is the calorie versus a kilojoule right there. You will notice that these packages actually do have to have kilojoules on them.
Bless you.
Okay, bless you. Yes, indeed. Okay, this is actually how you figure this out. You literally take the food item and you burn it inside what's called a calorimeter. And that releases all the energy, and then you can measure how much that water went up in temperature. Remember, the definition of a calorie is raising a gram of water 1 degree Celsius, right? Yeah. And so that's quite direct and easy to do. Okay. Note that this isn't actually done for every single food item. What ends up happening is sometimes most of these food items end up having to do this fats versus carbohydrates versus proteins anyways. And so they'll just go back through those and total those up. Okay? And again, there are tests to figure out how much fats, how much carbs, and how much protein is in something. Okay? The energy values for the 3 different types of food that we would ingest are these right here. So for carbohydrates, they have 4 kcal per gram. So that 1 gram of carbohydrates, that has 4 kcal, right? If you have 10 grams of carbohydrates, that would be 40 kcals, right? Okay. Fats, on the other hand, have 9 kcals per gram. That's a lot more dense energy, isn't it? Yeah. Proteins have 4 kcals per gram. As a human being, you probably should just go ahead and memorize this. Because I'm going to be honest, like, this is one of the more important facts that you can have in your life. It just is, right? Yeah. This is how you tell how much energy you're getting, right? Okay. Now, why do we have fats in our body, by the way? And we don't carry around a bunch of carbohydrates or proteins? Why do plants carry around carbohydrates and they don't carry around fats? Does a plant have to run away from stuff? No. And so plants carry their carbohydrates in their roots, and because it's a less energy dense substance, it tends to weigh a lot more to carry around that similar energy, right? And so the plants don't have to move around. Fine. But we have to, like, run from stuff, right? And we have to, like, move around. And so carrying twice the amount of weight for that same energy storage, that'd be a problem, wouldn't it? Yeah. Yeah. So, like, if we had used carbohydrates, you would weigh probably about, not quite double what you weigh now, but it'd be more like adding another 50% on you. Because you're not all fats, right? So it'd be a lot of extra storage. Okay, now, these are some different foods, and they're different carbohydrates and energies right here. Does everybody see those okay? Okay. Let me ask you a quick question. Does everybody remember the food pyramid?
Yes.
What was on the bottom of the food pyramid? Grains, and those have what in them? Carbs. And so they told you the thing you needed to eat the most was? Carbs. Exactly. And carbs are, do you know how many carbs you need? Are there any essential carbs? You ever heard of such a thing?
You don't technically need any carbs.
Yeah, you don't actually need to ingest any carbs at all. You will actually make all the carbs you need if you have the other stuff. Now, full disclosure, there's actually a bunch of genetic diseases and stuff that you try to do this, you can reveal in yourself and can cause you serious problems. And so I really would not actually recommend going completely no carbs. And it's actually somewhat dangerous to do without a doctor monitoring you. Okay? It's actually a terrible idea, though there's a bunch of conditions you can actually cure as well by going 0 carbs. So it's a weird thing.
Mm-hmm. You know, if you eat carbs before going to sleep, you can put on more weight.
Yeah.
Put on more weight. Eat it
So
before bed.
theoretically, the testing of that's been very inconsistent. Yeah.
Really?
Yeah. Oh yeah.
Oh, I gained weight.
Yeah. But anyways, that food pyramid, by the way, was completely a political thing. The best 14 nutritionists of the day came out in front of Congress, said, don't do this. You're going to create generations of people that have weight problems. They said it much less politely. And they were, of course, right? Yeah. And the government did not care. They blacklisted them and they destroyed their careers. Does anybody know why?
Because you need people to buy stuff.
Food subsidies, actually. So as a security measure against famine, the reason the United States hasn't had an actual famine, and we haven't been able to we've always been able to feed our population, even during the Great Dust Bowl, that still was not an actual famine in the United States for over 100 years, is because corn is super easy to grow in the U.S. Almost everywhere. And corn used to have subsidies to do that, and then you can grind it down, you can make high fructose corn syrup out of it, etc. Right? The store's great. In that time period, it became politically infeasible to do that anymore. And so what they did is they basically told everybody, you need to buy the corn that we would normally have subsidized and convinced you all to buy it. Anybody know what that got replaced with? We didn't stop subsidizing corn. Not at all. No. We continued doing corn. It got turned into ethanol and put in your fuel. And so the true master race of the United States is corn. That is what we do everything for. We do. Yeah. Oh, corn just grows so well in the U.S. Yeah, especially the genetic engineered varieties we have now. It's basically impossible to actually do a famine in the United States because of corn. Yeah, it's crazy. So anyways, nutrition. Does anybody have any questions on that so far? Okay, I'm going to leave you on this problem probably. What time is it?
It's 10:36.
Oh, cool. Okay, let's do this. So a cup of whole milk, this contains 12 grams of carbohydrates, 9 grams of fat, 9 grams of protein. How many kilocalories does a cup of whole milk contain? Now, while you start working on this problem, I'm going to point something out that's really funny. So the government got rid of the food pyramid. We did a food wheel, right? And that one's actually not terrible. Like, yeah, there's some argumentative points, but it makes sense. Does anybody know what we're now using? So the government released something. It's called a food guide. And it has a little website on it. You can look stuff up. Is this healthy for me? And it has a health score. Do you know what Lucky Charms is?
Cereal. Cancer in a box.
Yeah, it's really bad for you, right? And it's cereal, and it's marshmallows, and it's sugar, right? Lucky Charms has a higher health score than eggs. According to the United States government, Lucky Charms is healthy for you. Eggs are not healthy for you. When you start looking into these things, it just gets so wildly. Okay, so how do I do this problem? You're supposed to be working on the problem. Come on. So I have a table here, don't I? 4, 9, 4. Okay. Perfect. Exactly correct. Yeah, you got it. It's 12 times 4, exactly. And then 9 times 9. And then 9 of protein times 4, right? And that gives you your kcals for each of these. You add them all together. Perfect. Perfect. 170 kcals. That is exactly correct. You got it. Okay. Anybody have any questions about that? Fantastic. By the way, you actually really should know how to do this, because you'd be surprised where you'd find things wrong. Yeah. Okay. Okay. What time is it? 10:40. So I got 5 minutes. You're not getting out of here 5 minutes early. Don't even think about it.
Let's give a 20-minute break before next class instead of a 15-minute break.
Yeah, you don't need a 20-minute break. You get in trouble that way. Okay. So, right here we have the gender and the age categories. These are actually the activity ratings. And this is essentially, depending on your activity rating, how much calories you typically would burn. Now, remember that this was the average humans. Have you guys ever heard of the Pareto effect? No? Okay, the human distribution of abilities looks something like this. Okay? What that means is that if you go to the top, basically take the square root of a population. So out of 10 people, one person will produce 50% of whatever category you're talking about. So if you're talking about hit songs, 1 out of 10, 50% of the hit songs. If you're talking about the worst singing on the planet, 50% of the worst singing on the planet, done by 1 out of 10. Okay? Same thing for like lifting weights. There are people that are at least 10 times stronger than me on the planet. There are people that are at least 10 times weaker than me on the planet, right? In terms of lifting a weight. And so that's the Pareto effect. Now, we always take these averages right here and then talk about them. But keep in mind that in reality, there's a very significant population that's very, very far from that average, right? Yeah. So you do have to keep that in mind. There are people that burn 4,000 calories in a day. There are people that burn less than 1,000 calories in a day with moderate activity. And so it is, we talk about these things, yeah, it can get pretty crazy. Now, that is not the normal case. That is an unusual case, right? Okay. And so these are the common things. Yes, calorie counting does work. But you do have to keep that in mind that these average numbers may not be you. Okay? Anyways, this is some different activities and how much energy these things typically take. Notice that me, because I do sleeping, sitting most of my day, I burn calories very, very slowly. The lecturing does help a little bit. But I do walk up the steps, so that helps a little. But I really need to start doing some swimming and running. So the best thing could happen for my health is actually if all of you start having emergencies all the time, and I start having to run everywhere trying to put out fires on people, and that would make me really healthy, right? Okay. So we're going to go ahead and stop on this because I don't want to start on this and then you guys go, what the hell was specific heat? But you should go ahead and look at these things, try to get this in your mind, load it up, so I can start here next time. Huh?
Oh, I was telling them I thought I was on it.
Yeah, that sitting right here is killing you all, right? Only 100. Huh?
So long.
Yeah. Sit all day in these classes. That's why the lab, you have to stand.
I know, I was going to tell you about that yesterday.